Consider this graph. This can be colored using 5 colors. In other words, its chromatic number is 5. Now note the number of edge crossings in this graph. Only one in this case. We call this the crossing number of the graph. The crossing number of a graph have some really interesting properties. Like in this case, the crossing number is equal to the crossing number of a complete graph with 5 vertices. Now why is 5 important? Because this is the chromatic number of this graph. In general, if we have a graph with chromatic number r, then its crossing number is always greater than or equal to the crossing number of the complete graph with r vertices. We are representing crossing number as CR. Also known as Albertson's conjecture, this remains as an open problem till date. The conjecture is trivial for the cases when the chromatic number is 1, 2, 3 or 4, as the crossing numbers for all these cases is 0. Problem begins when it's 5 or more. In this video, we will have a look on some important observations and some related results. As we have been talking about crossing numbers and complete graphs, Richard K. Guy had conjectured that the crossing number of a complete graph can be estimated using this relation. Let's call this big expression f of n. He himself had verified the result up to n equals 10, and later it was verified for 11 and 12. But it remains as a conjecture as this limit isn't yet completely verified to be equal to 1. But this has been shown so far. Some of the related works have played important roles in the work progress. This expression is called the excess of a graph. It has been proven that for r greater than or equal to 3 and non-complete graphs, the excess of the graph is greater than or equal to r minus 3. For non-complete graphs with chromatic number r that have at most 2r minus 2 vertices have much larger excess. In other words, if the number of vertices can be written as n equals r plus p and p is between 2 and r minus 2, then the excess is greater than or equal to pr minus p square minus 2. If n is greater than or equal to r plus 1 and n is not equal to 2r minus 1, then the excess is greater than or equal to 2r minus 6. For r equals 5, the conjecture becomes the 4-color theorem, which states that any 2D map can be colored using 4 colors where no two areas sharing a common boundary have the same color. The case for r equals 6 was verified by Oporowski and Zhao. Albertson, along with Cranston and Fox, verified the cases where r is between 7 and 12.